Alright, I'm gonna try this again, dude. I tried recording this last night after work, dude, and it didn't go so hot because I also forgot stuff. But alright, let's get it. Okay, so Unit 6 with LO 6.01, right? It's talking about physical versus chemical changes. So physical changes, the chemical formula would stay the same. So like with these examples here, like with bending and compressing stuff, you're just changing like it's like a physical characteristic. You're not like if you bend like a piece of metal, it'll be the same piece of metal, right? When you compress something, it'll be the same thing, just compressed. Viscosity, this is a it's how thick something is. Like syrup is like very thick, difficult to stir. Uh, it's just a property or like a characteristic of it. Nothing to do with like chemicals. It's like syrup is just thick. It's still syrup. Boiling, freezing, melting point, or the phase changes. So like with this example with the water here, so we have H2O and then the parentheses L for liquid, going to H2O parentheses G for gas, right? It went from liquid to gas, but the thing is it's still H2O. So that's why it's a physical change, because the formula stays the same. So H2O is still H2O, even though it was a liquid, now it's a gas. So that's for physical. Chemical changes, though, the formula does change. So like burning stuff, rusting, digesting, these are all things that like break down like a chemical compound. So yeah, I mean, I got these samples from a practice test, so I'll make sure to, I guess, like just make a note of it in a sec. And with the formula changes, so like we have this 2NO2 here becoming N2O4, right? So yeah, they got the same number. So there's like two nitrogens here, two nitrogens here. Then we have 2 times 2, so that's 4 oxygens. 4 oxygens. Like, yeah, the number of nitrogens and oxygens stayed the same, but this is a different formula now, which is why it would be a chemical change. And there's a practice test for this, and it's like 6.01 on Blackboard, and it just goes through it just goes through like the same thing. It'll be like, is melting a physical or chemical change and stuff like that. Oh shoot, I didn't write that. I'm pretty sure melting's a phase change, so it would just be a physical change. Yeah, cool. So that's 6.01. Now we're gonna do 6.02 and 03, which is just balancing equations. So I kind of wrote the steps that like I usually do when I get to this point. When I get to this, so like it's just what I do. I don't know if it's like gonna be like right or not, but I did pass the test, so hopefully it works out. So first, want to convert the chemical names to the correct symbols, right? We're gonna be like counting like numbers and stuff. So if you have like C with like a number and then H with a number, or like and then like L or something. Mess like these numbers up, then like whenever you balance or like, because like balancing is just making sure there's like this the same number of like atoms or like pieces on both sides of the reaction. So if you mess up like then your counting is gonna be messed up too. Even if you did like, even at the end your counting was right. If initially the symbols were wrong, then it's like you kind of sold yourself, which is really unfortunate. So we just gotta try our best to not let that happen. All right, number 2, we're gonna organize organize the symbols from reactants to the left to products on the right, and then make sure we have this arrow, right? So this arrow, whenever you get this question on the test, you'll have like a type in text box on Blackboard. So to get this arrow, you have to press this like button. I don't know how to describe this symbol, but you click that button and it'll like show up like it'll give you a pop-up with all of the symbols, and you can just search for arrow, and then you'll be able to find this, right? So yeah, so reactants on the left, products on the right with the arrow. Okay, so once you have the symbols and you organized it, we gotta count and make sure that there are equal numbers of elements on both sides. Okay, so this is when I do it, I have like a kind of like a priority list, right? So this is my little like priority suggestion. So first is any other element that's not listed here. Okay, so if it's like Na, K, P, S, N, right? Count that one's first. Next, carbon if it's there, then hydrogen if it's there, and then oxygen if it's there. Okay? And I did make a little note here to be careful of the subscripts, right? And when we talk about subscripts, we're talking about like the number to the like bottom right of something, okay? So this is H2O, right? So for every molecule of H2O, there's going to be 2 H's and then 1 O, right? So if we have 2 pieces of H2O, that'd be 4 H's and then 2 O's. I'm pretty sure it, like, I don't know if maybe it's just because I got used to it, but it, yeah. I guess it's kind of self-explanatory, and if I keep explaining it, it might get more complicated. Just be careful, or like make sure you understand like what it means. So like this MgOH2, right? In one piece of this, there would be 1 Mg, and then since we have a OH, but there's 2 OHs, there'd be 2 oxygens and then 2 hydrogens, right? So whenever there's a coefficient of 3, this would make it 3 Mg, 6 O's, and then 6 H's, right? Because originally it was 1, 2, and then 2, right? So I'm not trying to make it any more complicated than it is. It's just be careful when you do the counting. Oh, and then here's a tricky situation that could happen. So one side, you have like an odd number, versus the other side, you have like this. Okay, so like here, we have 7 oxygens. And here, we have O2. So for every molecule of this, there would be 2 oxygens. And we got to figure out the coefficient so that we can get 7 on this side. Well, 7 divided by 2, that would be 3.5, right? And if we put this coefficient on there, right? 3.5 times 2, it does equal 7. But the thing is, we can't have this decimal point here, right? So what we're going to have to do is we're going to have to multiply both sides by 2, right? So the whole thing by 2. And this goes for even if there's like other coefficients in here. So like if there's like other pieces aside from just like O2, if it was like I don't know, like C6H12 plus O2, and then whatever the coefficient on there. So okay, hold up, let me write it out. So if it was like C6H12 plus O2 leads to like this, right? And like we said, this is like 3.5. But then we have to multiply the whole thing by 2, right? This would then be, hold up. This is just for a sample, or for an example. Like this isn't actually balanced, right? Because there's no carbon on the other side. But whenever you like multiply by 2, it would be like 2C6H12 plus 7O2 leads to that 2O7. Oh shoot, but I guess I hope my point got across. It's just that if there's a decimal point, or like whenever you're going through it and you get a decimal point, like a decimal point answer, you just have to double the whole thing, or like all of the coefficients, so that you can get rid of the decimal point. So yeah, but that's also just like if like the case is there. So just be careful. I might have made that a little too confusing, but I hope not. But hopefully it makes sense with the practice. And then last step, so after you have the correct symbols, you organize them, and you count to make sure they're equal numbers on both sides. Put phase labels. So to be honest, I'm not too sure or too confident on this part, right? Liquids, so indicated with the parentheses L. I know H2O is a liquid, and that's about it. Gas, parentheses G. I know carbon dioxide and O2 are gases. And to be fair, I guess other like covalent compounds would be as well, like maybe like SO2 or something like that, or like a hydrocarbon with like stuff that's like C5 and below. If it's like C4 H something, C3 H something, I guess they would be gases. But I'm gonna be real, dude. I'm really not sure. So I the thing is, like, when you're balancing, everything is like partial credit. So like if you get this right, you get this right, and you get this right, and this part's like you'll still get points for the other parts too. So I guess that's a good thing, especially since I'm not too sure on like this part. I'm not too confident on this part. So liquid, H2O, gas, CO2, O2. Solids, I usually just put anything that's ionic as a solid, or if it's like a metal element like aluminum or like, I don't know, sodium, I'll just put it's solid, or like lead. So yeah, I mean, I'm just really not too confident on this, but hopefully this, if the other parts make sense, hopefully it will balance out. Aqueous. So I this is usually like my filler, dude. I just say it's everything else. So like if it's ion, so if it's like Na plus or like Cl minus, it would be aqueous, because it can't like exist like normally. And usually everything else I'm not sure, I just put as aqueous. So yeah, so I was doing some examples and then I kind of messed up, so I had to re-record. So calcium, this calcium and gaseous chloride combined to make calcium chloride. So calcium, Ca, chlorides, Cl2, gaseous chloride is Cl2, and calcium chloride is CaCl2, because this has a 2 plus, this has a 1 minus, right? So order them from reactants, arrow, to products, right? Count, make sure there's 1 Ca here, there's 1 Ca here, there's 2 Ca2 over here, and there's 2 Ca2. So that's balanced, and then make sure to put phase labels. But yeah, and like, to be honest, like with this gaseous chloride thing, I'm pretty sure they'll give you the symbol, but I just wrote it out just so like just to, I don't know, make it a little harder, so like whenever the test comes, it might be a little quicker or a little easier to pick up, right? So next one, magnesium hydroxide reacts with hydrogen fluoride to make magnesium fluoride and water, right? So we got to write these symbols down. So magnesium's Mg2 plus, hydroxide is a polyatomic, which is OH1 minus. Hydrogen fluoride, it's two nonmetals, so covalent, so you just put them together, HF. Make magnesium fluoride, so Mg2 plus, F minus, so MgF2, and then water, H2O, right? Oh, and this is a MgOH, so yeah, 2 charge, 1 charge, make sure you put the parentheses to keep the polyatomic together, and subscript 2. All right, so if we look back to the priority list, so any other element, and then CHO. So let's look. So Mg falls in that category. So let's start there. So 1 Mg, 1 Mg. Cool, we're good there. Right? OH, that's for later. H is for later. F. There's 1 F here, but there's 2 here. So we have to put this 2 coefficient here, and now F is good. So are there any C's? There's no C's. Are there H's? There's H's, yeah. So let's count. So there's 2 here plus 2 here. So there's a total of 4. So 4 on this side. And here, we just had the H2 originally. We haven't gotten, this wasn't here before. So we just had H2. So that means there's only 2 on this side. So 4 versus 2. So we put this 2 coefficient here. So now we have 4 hydrogens and 4 hydrogens. All right. So hydrogen's done. So now we go to oxygen. Because so when oxygen is done less, usually, hopefully, if it was balanced, the balancing was right, it shouldn't be too, it's either going to be like done for you or it shouldn't be too difficult to solve. So let's see, there's 2 oxygens here, and then there's 2 oxygens here. So it's already balanced. So now that's done, right? Oh, and I forgot to put the phase labels, or maybe I just didn't get to it. So MgOH, so this is ionic, but MgOH. But I know OH is like, but that's kind of like cheating. I'm not, I won't lie, dude. I'm pretty not sure. I know this. I know this for a fact is liquid. MgF2. I'm fairly sure it's a solid. Hydrogen fluoride. I know it's, but that's like really cheating, because I know from previous experience that this is an acid. So I would put it like an aqueous, but like, dude, that's really, that's, I don't know how to teach that. HF. Because it's what? It's covalent. And I did say covalent is like, what did I say the covalent was? So, okay, never mind. I didn't put covalent on here at all. Sheesh, dude. Because I would also put MgOH as aqueous as well. Dang, because that's like, that's unit 7 stuff. So, sheesh. Alright. Maybe, dang, this is hard. Okay, I guess we could just hope that you guys don't get something like this, but if it's like a H attached to something and then a OH that leads to water, I would just put the reactants as aqueous. But that's like getting into unit 7 stuff. So I'm gonna just pray that y'all don't get that, because that's horrible. And that if anything, you got the symbols right? All the symbols are right, and the coefficients are right, dude. I'm pretty sure these phase labels, it's just, you got most of the points here, even if you mess that up. So, and plus, I don't even know if I'm right with the phase labels, because the book only has the balancing part. All right, moving on, dude. Okay, 1 pentanol is combusted / burned to make carbon dioxide and water. So 1 pentanol, so that's 5. So that's 1, 2, 3, 4, 5 with the OH here, right? Because it's 1. So this is H3, H2, 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 and H2. Okay. So that's C5, H2, 4, 6, wait, 3, no, 2, 4, 6, wait, yeah, 2, 4, 6 in the middle, 3, 3 on both sides. So 6 plus 6 is H12, and then there's an O. Okay. Is combusted / burned. So combustion / burned, all it just means it's whatever, it's something plus O2 gas. Okay. Or combustion is burned, yeah, to make carbon dioxide, so carbon dioxide CO2, which is gas. And then water H2O. Okay. Excuse me. Okay. So put this all together, right? So it'd be this C5H12O plus O2 leads to CO2 plus H2O. So boom, you got the symbols down. We organized it from reactants to products. So now let's count, dude. So how many? There's 5 carbons on the left, and there's 1 carbon here, so we're gonna have to put 5. Okay, so carbon's good. Now we'll do hydrogen. So there's 12 hydrogens on the left. There's only 2 here, so we're gonna have to put 6. So hydrogen's good. Now let's count oxygens. So there's 1, 2, 3 here, and there's, what's that? 2 times 2 times 5 is 10. 10 plus 6. Yeah, 10 plus 6. What is 10 plus 6? 16, right? 16, and here we have 3. So let's see. So I'll do some. So there's 16 on this side, right? So 16. We already have 1 here, and this one's still missing a coefficient. So let's see. That means we need to make this equal 15, right? Because the 1 on the left, so we can subtract that from the total of 16 that we need. Okay, so how are we going to make O2 equal 15? Well, 15 divided by 2 is 7.5. So this would be 7.5. But wait, dude, we can't have decimals. So we're going to have to multiply everything by 2. Okay? So that would be final answer 2 C5H12O. I'll just put, I'm pretty sure that's a liquid because the OH, it's alcohol from like a previous unit. Plus 15O2 goes to 10 CO2. O2 is a gas. Well, I should have spaced these out a little bit. My bad. O2 gas. And then CO2 gas plus 12 H2O. And if you multiply that out, that should still be balanced, right? So we got 10 carbons, 10 and then 10 carbons. We have 24 hydrogens. And we have how many oxygens on this side? 10 times 2 is 20 plus 12, 20 plus 12, that's 32. Here we have 2 plus 30. So yeah, all balanced out, dude. So that is a little 6.02, 6.03 balancing equations. No cap, dude. If I didn't look at the study guide, this would be the only thing I would freaking teach. Holy God. All right, let's move on. 6.04 and 6.05. So this is dissociation plus combustion reactions. So these are just reaction types, right? So once you know, like, what these types are, whenever they're like, oh, write this, like, for example, for dissociation reaction, write the dissociation reaction for CuSO4. Then you'll know what to, then you will know, like, what to write for the products and reactants, right? And you'll be Gucci. But okay, so let's start with dissociation. So for it has to be a soluble ionic compound. So meaning it has like any of these elements in it, right? And then the compound, like once you make sure it's a soluble ionic compound, the compound will split into its two parts. And that's all it is. So let's try it. Okay, CuSO4. So is this soluble? Well, it doesn't have any of the things up there, so we're going to go with the no here. NaOH? Yep, it is. So we can write, so since we know that it is a soluble ionic compound, we'll just split it up into its parts. So NaOH would lead to Na plus, and this would be aqueous, plus OH minus, which is also aqueous. It's all balanced. I'm gonna say this is aqueous because of the OH group, or because of hydroxide. Yeah, I'm really not too sure how to teach that part, man. So I'm sorry if you have. I guess you could take notes as to like what I write and how I write it. So maybe that would help. But I'm like really relying on just like my past classes on that one. So I'm sorry that I can't like teach that better. Okay, next one, MgCl2. We can see there's a Cl group in there, so we just gotta write it out. So MgCl2. I'm gonna say this is a solid, cause yeah, I guess it's no hydroxide. So MgCl2 solid. Then we get Mg2 plus aqueous because it's ion plus Cl Cl minus aqueous. Is that balanced? Well, there's one Mg on both sides. We just need to put a 2 here. Cool. KNO3. Yep, we got K and NO3. So KNO3 excuse me, aqueous is the K plus, which is also aqueous, plus NO3. Make sure you keep the ions, or the polyatomic ions, together. Minus. Okay. I just remembered something. So in the case where you have to fill it in, don't forget to put these charges depending on like what type of question they ask. So like, yeah, just be careful of that. I don't think I put in my notes on the other side, but just make it, yeah, just make sure that if they ask, or if they say like disassociates, or if they say like blank ion, or like something ion, then make sure you put the charge. Ca3P2. This is not soluble, so nothing. Cool. That's disassociation. Okay. Just make sure it's soluble, and then just split it into its two parts, which I know you guys can do. Okay. Combustion reaction. Combustion, it was mentioned earlier on like this bottom, I think this last one, right? I said combustion is just you're adding O2 to something, or you're adding, yeah, adding O2 to like a hydrocarbon. So that's just repeated over here. So combustion reaction, it's a hydrocarbon, right? So they'll usually tell you like the formulas, like C7H4 or something like that. They'll usually give it to you. I was just making it difficult before and like giving you the word name with like 1-pentanol. Like I'm pretty sure, yeah, I would strongly think that they will give you the hydrocarbon if it's like a combustion reaction. So you take this, it'll be given. Then you plug it into the formula. So all combustion reactions follow the same formula, which will be the given hydrocarbon, which is likely to be either a gas or a liquid, plus oxygen would lead to carbon dioxide and H2O. Okay. Oh, dude. Oh, I shouldn't have put. Fine, dude. I'll do the examples. Okay. So if they give us C7H8, I'm gonna write it. I'm gonna write it out, dude. So C7H8. I'm gonna say that's liquid because it has 7 carbons, and I think the cutoff is like 5 or more would be liquid, 4 or less is like gas. Yeah. Okay. Plus O2, and that's like if there's like no OH groups and stuff, but yeah, we'll just best guess it, dude, to be honest. Like it's a partial point for the phase labels. I don't know why I'm worrying too much. Leads to CO2 plus H2O. Okay. Gas, liquid. Okay. Now we count, dude. Starting with the carbons. All right. 7 carbons here, so we need 7 here. There's 8 hydrogens here, so we need a 4 here. How many oxygens? So there's 4 plus 14, so a total of 18. 18 divided by 2 would be 9. 9. Cool. Next. Gosh dang it. I'm hungry. Okay. C4H10. That has 4 carbons. I'm gonna say that's a gas. Plus O2 leads to CO2 plus H2O. Gas, liquid. I'm getting lazy. Okay, fine. Okay. Now let's count 4 carbons here. So we're gonna put 4 here. Okay, 10, H10. Excuse me. 10 hydrogens here. So we need to put a 5 here. How many oxygens? So we have, what's this? 8 plus 5. Gosh dang it, it's an odd number. 13 divided by 2 is what, 6.5? Okay. So this would be 6.5. And now we're gonna have to multiply everything by 2. So final answer would be 2C4H10 gas plus 13O2 gas leads to 4. No, not 4. 8. 8 CO2 gas plus 10 H2O liquid. Okay. Okay, last one, dude. Last one. Come on, Jeremy, you can do this. All right. Okay. C4H10O. So C4H10O. There's an oxygen in there, and it could possibly be like a OH or like an alcohol group. So I'm gonna just say that it's a liquid. Okay, plus O2 leads to CO2 gas plus H2O liquid. Okay, let's count carbons. So there's 4, hydrogens, there's 10, so 5. How many oxygens? Well, we have 5 plus 8. Gosh dang, it's odd again. So 5 plus 8, that's 13. So that's going to be 6 point. So that will be 6.5 again. So we're going to multiply multiply by 2. Get 2C4H10. Oh, I'm on. C4H10O liquid plus 13O2 gas. It's 8CO2 gas plus 5H2O liquid. Okay. Okay. So, yeah. So that was combustion reactions. So, hopefully now you will kind of know what to do whenever they're saying write the dissociation of NaOH of KNO3. Right, the dissociation reaction. Right. So once again, dissociation. Make sure it's soluble ionic and just split it into its two parts. Combustion. Just remember this formula, which is just hydrocarbon plus oxygen leads to carbon dioxide and H2O. And then once you write it all out, then you should be able to balance everything. Right? So that is 6.04, 6.5. Let's move on to 6.06 and 6.07. Okay. Now here we're talking about exo and endothermic reactions. Okay. So this is involving energy, right? So reactions, they either take energy or release energy. So exothermic is something that releases energy / heat. Okay? I don't know how you want to remember exo, exit, something that releases energy, however you want to memorize that. So here I wrote some ways that it could appear on the test, or like other ways that an exothermic reaction are represented. So there's this thing called delta H. It means change in heat, but it's written as triangle H, okay? And it would be a negative number, right? Big emphasis on this negative, okay? So exothermic, negative number, and I guess I'll just put the negative number kcal, because that's the unit that they usually give, okay? Remember, exothermic, negative, okay? They can also be written in like a reaction equation where you have the reactants, arrow product, and then it'll be a number kcal, so a number with the unit like k calories, kilocalories, right? So it just represents heat or energy, okay? So if your energy is on the product side, it's exothermic, okay? Next, they could say that the surroundings become warmer. Well, why would it get warmer? Well, it would get warmer because it's exothermic and it released energy / heat, okay? So something becoming warmer, exothermic. Combustion. So combustion, like these combustion reactions. Combustion is like, I want to say blowing up, dude. That's what comes to mind, dude. When I hear combustion, I think explosion, dude. So yeah, explosions are hot. They release a lot of energy. It's exothermic. Next, bond formation. So anytime there is a bond being made, it is exothermic. Okay. And there's a practice test here. I made a note of it. But yeah, I got you. And then the last way it could be represented is this little graph. So we're going to talk about this graph in a moment. But all it is just showing the energy over the time of like the reaction. Okay? So as the reaction goes forward, it shows you the energy changes. So on the left side here, we have the reactants. On the right side, we have the products. Right? And all it is for this, so if the reactants, or no, if the products are lower than the reactants, it'll be exothermic. Okay? So if the product side is lower and the reactant side is higher, it's exothermic. So I'm not sure. Maybe it would make more sense whenever I get to this part, but or it could be a little more confusing. But it is listed here as exothermic. So I guess just familiarize, or however you wanna, however it works for you, dude, because that's all that matters. All right. So that's for exothermic. Releases heat and it's written as these various things. Okay. So the opposite, endothermic. It absorbs energy or heat from the surroundings. So endo, I don't know how to, I don't know. In. Energy in. I don't know. I don't know. Whatever works for you, dude. That's the important part. But just know endothermic, it absorbs energy / heat from surroundings. So how would it be written? So we have this first thing with the delta H or triangle H. It will be a positive number with kilocalories. Okay? Positive number. Exothermic was negative. Okay? It could also be written in the reaction / products form, but this time it will be on the reactant side. Okay? Because the exothermic was on products. So reactants will be on, or for endothermic, this would be on the reactant side. Next way, surroundings get colder. So if it's like an ice pack or something, that would be endothermic. And then bond breaking. So if you're breaking bonds, it takes energy to break a bond, right? So yeah, bond breaking is endothermic. Bond formation is exothermic. And then here's a graph again for this time for endothermic. So here, right, your reactants are lower than your products. So this is endothermic. Okay. So there's a 6.06. There's this practice test on Blackboard that goes over this, or that gives you practice. It's also where I got like some of these examples from. So yeah, hopefully that works out pretty well. Dude, I'm getting so hungry. So that's 6.07, 606, 607, right? Now we're gonna talk about 608. 608 to 610. Oh, I'm stupid, dude. This is supposed to be 6.10. Whatever. This is the reaction energy diagram. So we're going to be talking about it. The thing is, like, I checked the study guide, right? And it was like these LOs would not be on the core exam. But I have no idea why I keep, like, I was going to skip it, but I don't know why I felt uneasy skipping it, even though this is only on the STA. So I'm not sure. Maybe it would just help out whenever you get, like, other stuff. But it could also make it more confusing. So I'm not sure. But based on what she has on her course, on her org site, these LOs are not included on Core 6 exam. But I'm going to still go over it. If you want to skip it, just skip it. So what is the energy diagram? It's this thingy, the thing I showed you earlier. This with the loop. Okay. So once again, on the left side we have energy, and at the bottom we have like reaction time, or like just the progression of the reaction. Okay. On the left we have reactants. On the right we have products. Now there's different parts. We're gonna be talking about this and this. Okay, so there's going to be a hump. There will always be this hump from reactants before it gets before the reactants goes to the products, it has to overcome this like threshold called the activation energy, right? Once it gets like over this activation energy, right? So practically like this hump, once it gets over that, then the reaction can continue to the products. Okay? So activation, and it must be overcome for a reaction to progress. Okay? So if, yeah. So once the reactants overcome this energy hump, then they can become products. So this delta H that we were talking about earlier, it is the difference, is the change from reactants to products, right? So here, the products are higher than the reactants, so it would have a positive, right? It went higher. It has a positive delta H, which means it would be a endothermic. This is an endothermic graph, okay? So I hope that made sense. So this reactants have to overcome a hump before they become products. What's that hump called? That's the activation energy, right? And then the differences in like the energy levels between the reactants and products, indicated by this, is your delta H. And since the products end up higher, it's positive, so we have an endothermic reaction. Okay, I hope that made sense. So now we're going to talk about this thing called a catalyst. Okay, so what is a catalyst? I'm pretty sure you've heard of catalyst used in like a different sense, maybe in like in like books or like video games or like news articles or whatever. All a catalyst does here, so kind of the same graph, we have the hump and the reactants on one side, products on the other. Okay, so this was our original activation energy, and this is the activation energy with the catalyst. The catalyst reduces that hump that the reactants have to go through. Okay, so before it would have to go all the way up here, but now it can just go here, right? It lowers the activation energy needed for a reaction. So since this hump is smaller, it would make it easier for the reaction to go through. So it's easier for the reactants to become products, meaning the reaction rate is faster. So yeah. So here's some additional like reaction rate factors or things that can like affect it. So if you increase temperature, right, you're increasing the collisions, the reaction will go through faster. But don't get this switched up with the is it solubility? I think from like a previous unit. We're talking about reaction rate here. We're not talking about like solubility, okay? So increase in temperature will always increase the reaction rate. Increase pressure, more collisions, increase concentration. Increased concentration means there's like more stuff in the solution, so like higher percent stuff. That just means there's more things to collide. Grinding / chopping solid pieces. So yeah, if you like cut it into smaller pieces, there's more places for the reaction to occur. Steering, so like that's like you're making more collisions, and then adding the catalyst once again, which lowers the activation energy. So yep, so that's catalyst. So we talked about how this graph works, the different axes, activation energy, as well as the delta H. So here we have a different example here, dude. So I left some stuff out, but I'm pretty sure you can. So this is energy, and then reaction progress. That reactants are on this side, products on this side. Okay, so All right, let's start with this delta H. So you can see the products went down. So delta H would be negative. So this is a exothermic reaction. Okay? Now, what is this yellow line representing? It is representing the original activation energy needed. And then what is this green line showing then? Well, it's showing the activation energy with a catalyst. And yeah, I don't know, dude. I really can't remember if it was on course 6 or not, but I feel really uneasy if I didn't talk about it. So anyway, yeah, that's the diagram with like reaction rates and then catalyst. All right, now we're on to the last part, dude. Last part. Equilibrium. Okay, so what is equilibrium? So some reactions are reversible, okay? And they're indicated with like these like two-way arrows, okay? So it means that there can be a forward reaction as well as a backward reaction. So forward reaction would be the reactants going to the products. Backward reaction would be the products going to the reactants. Oh, like products going to the reactants, okay? And a key thing to know about this is that both them, the forward and backward ones, they have the same reaction rate. So I'm not sure how that will show up on the test, but yeah. So the reaction rate going this way is the same as the reaction rate going this way. Okay. So I guess I don't really have any examples here. I'm not too sure. So like, let's see. Maybe I could make one really quick. Yeah. Okay, we can try. Okay. So that's like, let's look at this. So we have H2O, because this is gonna like lead into core 7. H plus OH minus. Okay. So we know that there's a forward reaction as well as a backwards reaction, right? So in a sample, if they're asked like, what is present in this sample, right? Well, the answer would be everything, right? Because it can go both forward and backwards. So you're going to have some of both. So, like, if you imagine, right, you put some H2O in, like, a container. So there's some H2O, there's none of this stuff. Then the reaction is going to go forward, right? And as it goes forward, the amount of this increases, the amount of this increases. And then it will, like, start slowing down, right? Because equilibrium, it has to be, like, it references, like, being equal. So once there's, like, equal amounts of this stuff on both sides, then, like, neither reaction, they just cancel each other out. So, okay, that might have been a little confusing because I kind of went a little too forward. But all I just wanted to get across was that in an equilibrium reaction like this, you're going to find everything present. There'll be like some of this and then some of this. It won't just be like these ones with a straight arrow where it'll turn from this to this, like, permanently. Okay? That might have been a little confusing. So, yeah, equilibrium, there's forward reactions and then backwards reactions, just meaning that both the reactants and the products will be present at, like, any time. Okay? So, what is present in a sample? Everything. Reactants and products, because of equilibrium. Okay. So now this question is like I'm not sure if they'll ask this or not, but like I can't think of any other questions to ask regarding equilibrium. So forward or backward reaction favored. So if they're like so if ever they're like, okay, is the forward or the backward reaction favored in this equation? Yeah. Okay. So dang, dude, I'm really like not going off much here because I swear I can't remember anything, but this was the one of the LOs, so we're gonna talk about it. So is the forward or the backward reaction favored, right? We can take this as our example. Sheesh. No, dude. Okay, we can take this as our example, okay? So whenever we're talking about which reaction is favored from the forward or the backward, I like to think of it as a seesaw, right? So where you have your reactants on one side and your products on the other. So if you have more reactants, right, the seesaw on the reactant side will go down and the products will increase. Or we'll get like, yeah, well, the products will increase, right? So forward reaction would be favored. But if there's more products, right, then the product side will go down and the reactants would increase, meaning the backward reaction is favored. So, yeah. So, like, in this case, let's say, like, oh, you had an empty container and you put some water in it. Which reaction would be favored? Well, since you just put water in it and there was none of this, right? There's going to be reactants, lots of reactants, but no products. So the products are going to increase. So forward reaction favored. Oh, so what happens if this equation gets like to equilibrium, right? It gets to equilibrium and then the forward and the backwards rate, they like cancel each other out. So that's equilibrium and you have like equal amounts of this and this. Oh, shoot, dude, it's not even balanced, bro. Oh, no, it is balanced. Like, I'm tripping. Okay. So I guess the equilibrium, but I decide to add more OH. So I want to increase this amount. Well, there's more products. There's more products now. So it would go to the reactants, meaning the backward reaction would be favored. All right. But, like, dude, I'm like, very, very like shaky or I'm like not too sure for real. So because I really can't remember questions about this on core 6, so I really don't know. But yeah, those were the LOs on unit 6, right? I hope this helped. And I get I'll send, I guess I could post this as a PDF on the YouTube video whenever it uploads. So yeah, I hope that was helpful and working, dude. And I hope you guys all pass or like at least get the grade that you would like. So yeah, text me, I guess, if there's if there's any problem, if you have any questions and stuff. And maybe I should get working on 7 because I'm literally done with the class except for the final. All right, good luck, dude.